Hi there guys, welcome to this video where we're going to take a look today at a 6th term examination paper problem. So we're going to get straight into it today. We're going to be looking at the 2018 Step 3 paper, and it's going to be question 7 that we're going to be looking at. So this is a nice little problem, challenging. It took me a while to figure out the solution to this problem, but that's how it is sometimes. One thing that you're faced with when trying to find the solution to a non-routine and genuinely challenging problem is that you'll find that much of the time and effort that you have to put into finding a solution to that problem is actually trying to find the right way to actually view the problem and interpret the information that you've been given and so on and so forth. Once you get on the right track, what you'll find is that the solution often almost writes itself. And when you look back over what you've done, you think, how did it take me so long to see this? It's so straightforward. But that's how it is. Okay, and that's what happened to me. So this is just, that's how it is with problem solving. There's nothing you can do about it. You've just got to develop your own strategies for dealing with that kind of situation. Okay, how you deal with that situation, I can't tell you exactly what you need to do. You've just got to gain experience at solving problems, and it will still happen to you. And unfortunately, yes, it could happen to you in an exam, but the more practice you get at solving problems before you get to your exam, the less likely something like this is to happen. Okay, that's the so if you feel a bit disconcerted about the fact that this could happen in an exam, there are things that you can do to try to mitigate against that possibility as much as possible, but it involves doing a lot of work before you get to your exam. And even then, there's no guarantees, okay? Nevertheless, let's have a look at the problem. So it's a Step 3 paper, so it is going to be touching on further mathematics material. So complex numbers, de Moivre's theorem comes up. You're going to have to be quite confident with manipulation of inequalities. So if you're not doing further maths, then you're going to struggle a little bit unless you've done some kind of independent research and independent work and reading around the subjects and things like that. Step 3 is typically aimed at further maths students, A-level further maths students. So let's take a look anyway. So 2018, Step 3, Question 7, I'll leave a link in the description to this video so you can download the paper yourself, because I'm not going to be writing everything on the board necessarily. Okay, let's have a look anyway. So part I, there's three main parts to this problem. So part I is use de Moivre's theorem to show that if sine theta does not equal 0, then this equality holds for any positive integer n. Okay? So, we're told to, as with many step problems, the first part is often it's kind of easing you into the problem. It's much more straightforward. In this case, so much so that we're actually told what to do, or we're given a very big hint. We've still got to figure out for ourselves how we're going to use that hint, but nevertheless, we've been given a big hint about what to do. Use de Moivre's theorem, okay? So, what's de Moivre's theorem? Just a quick reminder. So de Moivre's theorem says that if we've got cos theta plus I sine theta is our trigonometric form of a complex number to the power of k. And I'm going to assume, because we're dealing with positive integer n here, I'm going to assume that k is a positive integer. De Moivre's theorem does apply for negative integers as well, and other values, but we're going to stick with positive integers for now. Then de Moivre's theorem says that cos theta plus I sine theta to the power of k is equal to cos k theta plus I sine k theta. It's almost magic, okay, that this power of the k, power to k here actually allows us to just effectively simply multiply the arguments of the trigonometric functions here. Okay. Because we're dealing with positive integer k, I'm going to state another version of de Moivre's theorem, which is cos theta minus I sine theta which is going to give cos k theta minus I sine k theta. Okay, so those of you in the know will realize that both of these could be combined basically into a single statement and just allowing k to range over integers rather than just positive integers. But because we're dealing with specifically positive integers here, we're going to restrict ourselves to, I'm going to split it into two separate versions. Okay, right, so coming up to this now then, what this suggests is that we start with the cot theta plus I. Make sure that you're familiar with trigonometric functions, cot, tan, things like that, because this is equal to cos theta over sine theta plus I to the power of 2n plus 1, which is equal to, so okay, pay close attention here. It seems obvious, but it's easily missed. We've got 2n plus 1 factors of this. So I'm going to pull 1 over sine theta out as a common factor from each one. That means that I'm going to be doing this 2n plus 1 times. So I get sine to the power of 2n plus 1 theta, cos theta plus I sine theta to the power of 2n plus 1. This is where De Moivre's theorem comes in. Cos 2n plus 1 theta plus I sine 2n plus 1 theta. Piece of cake. Okay. Similarly, cot theta minus I to the power of 2n plus 1 is going to, using a similar argument, except here I'm going to get minus I sine theta. I'm going to get 1 over sine 2n plus 1 theta cos 2n plus 1 theta minus I sine 2n plus 1 theta. And really I should have put some brackets around that. Okay, so we're wanting to do this, take away this. Okay, forget about the 2i for now. So this take away this is the same as this take away this, which is going to be 1 over sine to the power of 2n plus 1 theta cos 2n plus 1 theta minus cos 2n plus 1 theta, 0. That's a nice little bit of cancelling that we can do there. I sine 2n plus 1 theta minus I sine 2n plus 1 theta is going to be 2i sine 2n plus 1 theta. So therefore the numerator here is just equal to this. Notice that I've got the 2i here. So when I divide by 2i, what am I going to be left with? I'm going to be left with sine 2n plus 1 theta over sine to the power of 2n plus 1 theta. Easy peasy, right? No problems whatsoever. That's where it ends, okay? The simplicity ends. Now we're kind of left to our own devices. We're much more expected to be much more self-reliant from this point forward, okay? And it really does make a difference. This is very typical of step problems where you're kind of eased gently into the problem and then boom, okay, something changes, now you're on your own and you're just given something to do. And in contrast to maybe the normal A-level kinds of problems that you'll get on exams, where you're given something to do and you're always kind of nudged in the right direction. It's very, very overt in many cases. Here, it's just you're given something to do. Okay, just do it. Okay, you've got to figure out how to do it. Right, so we've done that. So now we're on to the next bit, which is as follows. I'm just going to have to write something up here. So 2n plus 1 choose 1 x to the power of n minus 2n plus 1 choose 3 x to the power of n minus 1 plus minus 1 to the power of n equals 0 cot squared m pi over 2n plus 1 m equals 1, 2, 2n. Okay. So then it just simply says, by the way, I will keep looking down here because that's where the question is for me. Given that we've just done that, deduce that the solutions of this equation are this for these particular values of m, okay? So the equation is 2n plus 1 choose 1 x to the power of n minus 2n plus 1 choose 3 x to the power of n minus 1 plus up to minus 1 to the power of n equals 0. The solutions are evidently x equals cot squared n pi over 2n plus 1 for m equals 1 up to n. Okay, so let's have a look at how we're going to do this. So this took me a bit of time to figure out. Actually, no, it didn't take me time to figure out. It took me time to decide to do what I needed to do. And this is a situation that you might find yourself in when it comes to solving problems sometimes, whether you're in an exam or whether you're not in an exam alike, where on the one hand, you've got an idea about something that you know you can do, but you know it's going to be quite time consuming to do it. It's going to be quite messy. It's going to be quite fiddly. And you've just got a general reluctance to do it. Maybe you're just feeling a bit lazy or whatever. On the other hand, you think, well, the grass is greener. Okay? There's probably a better way to do this. Something that involves less algebraic manipulation. It's only going to take a couple of lines. But I haven't thought of it yet. So I can either go for my original idea, just get stuck in, actually get going with it. I know that I'm going to be able to do it. It's going to get the job done. It's just, I'm going to have to give myself a bit of a kick up the arse. Okay? On the other hand, I can kind of root around for a better way of going about solving this problem, which there may be, there may not be. Okay, there's no guarantee that there is a better way. I might get lucky, right? And I might find something very quickly, an alternative solution. And I'll think, well, how much time I've saved here. On the other hand, I could end up spending a lot of time trying to find something else and either just not finding something else because I just can't think of something else, or not finding something else because there actually isn't anything else that I can do or anything sensible I can do. So in that case, you could end up spending a lot more time trying to find a quicker way of doing something than the time that you would have spent just actually getting on with things in the first place using this, what you perceive to be a less efficient method. There's no right or wrong course of action here. You've got to decide in the moment how you feel about this. There have been times in the past where I've decided that I don't want to go down this route. I want to try to think of something else, and I've got lucky and I've managed to think of something and it saved me a lot of time. On the other hand, as is what happened here, I was feeling a bit lazy. I didn't really want to go through the algebra. I thought maybe there's a quicker way of going about it, and I spent probably 10-15 minutes trying to think of something else, and came to the conclusion that I wasn't getting anywhere. Okay, fortunately I'm not in the exam. I've got the luxury of not being in the exam and not having exam pressure, so I can sit around and think about these things if I really want to. In an exam, it's up to you how you deal with this situation. I can't tell you what to do. You've got to decide for yourself how you're going to deal with this situation. Are you going to put a time limit on something, or are you just going to get on with your original idea? It's entirely up to you. Sometimes the best thing to do is just get on with it. Okay, that's what I should have done here, and that's what I'm going to do now. Okay, so also what I'm going to write on the board is not necessarily everything that I actually wrote out on the page. Okay, all of my work. I'm going to give a good idea of what kind of algebra was involved, but without necessarily going into fine detail with absolutely everything. So, but having said that, in your exam, don't try to skip steps, okay? If it comes down to it, if you think it's going to help you to keep track of things better, to put a couple of intermediate steps in rather than taking a big jump in your algebra, then do so, okay? You're going to save yourself a lot of hassle in the long run, and this is a lesson that you might have to learn the hard way. Hopefully not, but you might have to learn this the hard way, that yes, if you try to skip steps and you take big jumps and things like that, you end up making mistakes and having to go back anyway and just fill in those gaps that you kind of missed out. But also, you have to write in such a way as to sufficiently clarify your solution, your idea to your examiner. Okay? So let's have a look then. So on the one hand, we've got, so my idea was, by the way, I don't think I actually said what my idea was. My idea was to use binomial expansion on this and this. The thing that gave me the clue is the fact that we've got binomial coefficients here, right? Binomial coefficients, very obviously binomial expansion. It's just I was feeling lazy, didn't really want to do it, but that's what I really need to do. So cot theta plus I to the power of 2n plus 1 is equal to, hopefully you know your binomial expansions and binomial theorem. If you don't, get it sorted. From r equals 0 to 2n plus 1, 2n plus 1 r, I to the power of r times cot 2n plus 1 minus r theta. Okay? And this is very normal on step exams, by the way, to have this sort of algebra involved, having to write out these sorts of algebraic expressions. So cot theta minus I to the power of 2n plus 1 is 2n plus 1, choose r, and it's minus I to the power of r cot 2n plus 1 minus r theta. Forget about the 2i for now. So we need to do this minus this. So this minus this, this minus this is going to be equal to the sum from r equals 0 to 2n plus 1, 2n plus 1, choose r. And it's going to be I to the I squared, I to the power of r minus I to the power of r times cot 2n plus 1 minus r theta. Okay? Easy peasy. Right, so what I need to do is I really want to sort this thing out here. Okay? So let's have a look at just some powers of I and powers of minus I. So I to the power of 0 is equal to 1, minus I to the power of 0 is also equal to 1. I to the power of 1 is equal to I, minus I to the power of 1 is equal to minus I. I squared is equal minus 1, minus I squared is equal to minus 1. I cubed is equal to minus I cubed is equal to minus I to the fourth is equal to 1, minus I to the fourth is equal to 1 also. So those of you familiar with I, complex numbers, things like that, this is no surprise to you. This is nothing new. But the point is that even powers of, for even powers, we've got equality. I to the 0, minus I to the 0, both equal to 1. I squared minus I squared, both equal to minus 1. I to the fourth, minus I to the fourth, both equal to 1. And we'll just keep cycling through these values, okay? 1i, minus 1, minus I, 1i, minus 1, minus I, 1i, and so on and so forth, and similarly over here. But then for odd values, I to the power of 1 is equal to I, minus I to the power of 1 is equal to minus I. We've got opposite signs, okay? This is going to be important for what's going to be going on here. Because what we see then is that for even powers of r, this is going to be equal to 0. For even powers. So what's going to be left? We're going to have, and it's going to be 2n plus 1, choose 1. I to the 1, let me do it here. I to the 1 minus I to the 1 is going to be I minus I, which equals 2i. So 2n plus 1, choose 1, 2i, cot, r is equal to 1, so it's going to be cot 2n theta. Next one. When I is equal to 2, that disappears. This is a good sign, by the way, because notice that we've only got odd numbers in these binomial coefficients. We've got 2n plus 1, choose 1, 2n plus 1, choose 3. The next one will be 2n plus 1, choose 5, and so on and so forth. So we're going to get 2n plus 3, 2n plus 1, choose 3. And we've got I cubed minus I cubed, which is minus I minus plus I, or minus I, which is minus 2I. So we're going to get minus 2I cot 2n, I'm going to write it as 2 times n minus 1 theta. So this is going to continue all the way down. Now we get to I to the 2n plus 1, which is equal to I to the power of 2 to the power of n times I, which is minus 1 to the power of n times I. And I to the power of minus I to the power of 2n plus 1 is equal to minus I to the power of n times minus I, which is minus 1 to the power of n times minus I. So therefore, this, take away this, is going to be 2I times minus 1 to the power of n. Okay, so here we're going to get plus 2I times minus 1 to the power of n. Okay, so I'm flying through the details of this quite quickly. I'm really just trying to give a rough idea. I'm not going through in too much detail the exact steps in my algebraic manipulation. I'm going to leave you to a certain extent to fill in those gaps yourself, because I feel that if you're doing further maths, you should be confident enough to do stuff like that. If there is anything that you're not clear about, then do ask in the comments section, and I will provide some clarification. But obviously, I'm trying to make this presentable to a certain extent, rather than getting bogged down with all of the details and everything. Okay, so this is effectively the numerator of this expression here. Okay, so now if I divide this by 2i, what will I get? I'll get, that will disappear, that will disappear, that will disappear. And what do I get? I effectively get this equation. Okay, I get this equation with x equal to cot squared theta. If I replace the cot squared theta with x, then I get this equation. Okay, so notice that cot 2n theta is cot squared theta to the power of n, x to the power of n. That's why I wrote it in this particular way. So this, well, okay, the left-hand side of this equation are identical, provided that I set x equal to cot squared theta. So what we've deduced then is that this thing here, this expression here, is equal to this, which in turn, with this substitution, is equal to this equation, or at least the left-hand side of this equation, should I say. So if this equation is equal to 0, that means that if we can set this equal to 0, and therefore this must be equal to 0 also. Okay, so let's have a look then what happens when we set this equal to 0. So this is where the deduce bit of this problem is. So we showed this was true, and then we were just simply told to deduce that the solutions to this equation are these. And that's what we're left to figure out, okay? So let's have a look. We don't need this anymore. Get rid of that. Get rid of that. So, if we set sine 2n plus 1 theta over sine to the power of 2n plus 1 theta equal to 0, this means that sine 2n plus 1 theta is equal to 0. Okay? And therefore, 2n plus 1, theta, 2n plus 1 theta must be equal to 0 or plus minus pi or plus minus 2 pi, and so on and so forth, okay? So in other words, 2n plus 1 theta must be equal to m pi, for m is an integer. But that's too many. That's too many values of m, right? Evidently. Because we're told that these are the solutions to this equation for m equals 1 to n. So what's going on here? Why have we got so many values of m? Well, okay, we've got to show how these values of m are going to have to be restricted, okay? Rather than having m is an element of the integers, we've got to show logically how we can whittle things down to this. And you do have to show this. Do not be tempted at this stage to say, well, okay, I'm just going to stick m equals 1 to n in here rather than m is an integer, okay? Because the logic tells us from here to here that m is an integer. Now, there's other things that are going on that we need to take into consideration. We need to show how we've taken them into consideration to get things down to m equals 1 to up to n, okay? You do need to show this. Do not try to fool your examiner. Do not try to pull the wool over your eyes of your examiner. For the simple reason that even though you're doing a step 3 paper, which suggests that you've probably got a talent for mathematics and you're probably very good at mathematics, you are not as good as your examiner, okay? Not at this stage. Maybe further down the line you will be. When you've gone through university and you've done graduate study, postgraduate research and stuff like that, maybe further down the line, some of you will be. But at this stage, you're not, okay? So you can't fool your examiner. So don't try to slip in some illogical steps thinking that your examiner's not going to notice, because they absolutely will notice, because it's so blatantly obvious. And if it's not obvious to you at this stage why it's obvious, it will be in a few years' time. Once you've done some mathematics at university, you'll see straight through these sorts of things. Okay, so let's get rid of that. How can we get these values down there? So there might be all different ways of justifying this, but you've just got to justify it in a suitable way. Right, so let's have a think about cot m pi over 2n plus 1. Okay, so by the way, this means that theta can be equal to m pi over 2n plus 1 for m is an integer, if that makes it any easier. So if m is equal to, let's say m is equal to 0, or it's equal to 2n plus 1, 2n plus 1, yeah, 2n plus 1, or 4n plus 2, or 6n plus 3, or in fact, k times 2n plus 1. Where k could be positive or negative, by the way. Positive or negative integer. What happens? Well, in this case, we get cot 0. Or we're trying to evaluate cot 0. In this case, we're going to be trying to evaluate cot pi, cot 2 pi, cot 3 pi. We'll go the other direction, cot minus pi, cot minus 2 pi, and so on and so forth. Do you see the problem here? Cot is not defined at these values. 0, pi, minus pi, 2 pi, minus 2 pi, and so on. So none of these are possible values for m, because cot m pi over 2n plus 1 is undefined at these values of m. Okay, so that gets rid of those values. So m is no longer an integer. M can still be an integer, just not these particular values of integers. But now let's have a look at the values m equals 1, 2, 3, up to, let's say, 2n. Okay, So in that case, what do we get? We get the values cot pi over 2n plus 1, cot 2 pi over 2n plus 1, up to cot 2n pi over 2n plus 1. Okay, and because of the shape of the cot graph, well, this is going to be greater than 0. So 0 is going to be less than this value, and this value here is going to be less than pi. So we're fine then. We've got values, all of these values, pi over 2n plus 1, 2 pi over 2n plus 1, and so on, are all between but not including 0 and pi. So if you think about the graph of cot, it's decreasing, okay, and it's strictly decreasing. So all of these values are going to be distinct. And how many of them are there? Well, at the minute we've got 2n, which is still too many. But what happens if we continue? So we've already excluded 2n plus 1. What happens if we go to 2n plus 2? If we go to 2n plus 2, then cot 2n plus 2 of pi over 2n plus 1 is equal to cot of pi plus pi over 2n plus 1. Now, another thing about the graph of cot is it's got a translational symmetry. Oh, it's periodic. Its period is pi. It repeats itself exactly every pi radians. Okay? So in other words, cot of pi plus pi over 2n plus 1, which is this, which corresponds to this value of m, is equal to this value of cot. Similarly, cot of 2n plus 3 pi over 2n plus 1 would be equal to cot 2 pi over 2n plus 1. Cot 2n plus 4 pi over 2n plus 1 would be equal to cot 3 pi over 2n plus 1, and so on and so forth, right? So in other words, all of the values, 2n plus 2, 2n plus 3, 2n plus 4, are all just repetitions of the values that are obtained from these. So I can scrap all of those. 4n plus 2 has been scrapped. What about the next lot? Well, again, it just kind of cycles through the values that I obtained from here. I can scrap them, and I can keep doing this, and I can scrap all of the values from 2n plus 1 inclusive onwards, and similarly going in the other direction. Okay, so cot of, if I chose m equals minus 1, that would give the same value as if I plugged in 2n. Minus 2 corresponds to 2n minus 1, and so on and so forth. So I can scrap all of those values. So now I'm just left with these possible values of m. And yes, you do need to show this kind of stuff. You need to explain this kind of stuff. I'm not saying that this is the only way of explaining this and justifying it in a suitable way, but whichever way around you go about things, you have to show it in a suitable way. Okay, so we've still got too many values though, because we've got the values of m from 1 to 2n. We need the values from m up to n. We've got twice as many values as we need. Another thing that we can use is the rotational symmetry of cot about pi by 2. Okay, so here's pi by 2, 0, pi, x, y, whatever. So the first n values of m, 1 to n, are all going to give values of, in here, so m pi, for a value of n, m, between and including 1 and n, m pi over 2n plus 1 is going to be less than pi by 2. Okay, so we're going to get m equals 1, 2, 3, up to n. Then once we get to n plus 1, we jump over at pi by 2 and we get to here. n plus 1, n plus 2, up to 2n. Now by the symmetry, the rotational symmetry here, the value that I get when I plug n plus 1 in here is going to be the negative of the value that I get when I plug n in here. The value that I get from n plus 2 is going to be the negative of the value that I get for n minus 1. So for every value that I obtain here from each of these values of m, from 1 to n, these will be the negative. Each one will be the negative of one of the values from n plus 1 to 2n, and vice versa. Why is that important? Well, that means that I can scrap the values from n plus 1 up to 2n because of the square here. Okay, because what I'm using here is the fact that about pi by 2, because of the kind of the oddness of cot, I guess, in a way. If I've got cot, what shall I use? Cot phi, pi by 2 minus phi is equal to minus cot pi by 2 plus phi. Then the squares are going to be equal. So cot squared pi by 2 minus phi is going to be equal to cot squared pi by 2 plus phi. Okay, so that's the idea that I'm using, this rotational symmetry about pi by 2. Okay, great. So that means that I can get rid of the values from n plus 1, n plus 2 up to 2n. So I've got things down now to n is just equal to 1 to n. Okay, which is what I needed. So it is important that you go through this kind of deduction. How you present it is entirely up to you. Like I said, I'm just giving kind of the ideas here, rather than actually presenting everything here as if I would be writing it in an exam, in which case I would be going into much more detail, being much more explicit. I'm leaving you to fill in some of the gaps. Okay? So we're done with that part of the problem. So now let's move on. So we need to deduce that, or hence show that, the sum of cot squared m pi over 2n plus 1 from, what is it? M equals 1 to n is equal to n times 2n minus 1 over 3. Okay, I've already dropped a big clue, I think, if I remember rightly. Thinking what I said earlier about this being a polynomial. If I mentioned that, if I didn't, forgive me, but I think I mentioned something about this being a polynomial, in which case I was dropping a big hint about what to do here. Okay, for this part. So this is part 2, by the way, or part II. Now, I spent a while thinking about this because I completely overlooked this. I recognized that this was a polynomial, but there was something that it just didn't click with me straight away. Again, this is just something that happens in exams or when you're trying to solve problems. You've just got to sometimes be patient until you find the right way of viewing something. So, I don't think, what did I try to do? Nothing useful, to be perfectly honest with you. I was kind of noodling around a little bit with some algebra. Probably took me a good 10-15 minutes to figure out what I needed to do here. It shouldn't have taken that long, if I'm honest with you, and this is how it is. Sometimes you're kicking yourself, because it's once you see things in the right way, you see how obvious it is, and you're just kicking yourself. But anyway, the big clue here is that these are the solutions to this equation. They're the roots of this polynomial. We could call them roots. Now, if you remember, if you've got, for example, I don't know, a cubic, ax cubed plus bx squared plus cx plus d with roots alpha, beta, and gamma. Hopefully you've seen this kind of stuff before. The sum of the roots, alpha plus beta plus gamma, we don't need to know the values of these, by the way. Alpha plus beta plus gamma is equal to minus b over a. In other words, the value of this coefficient of x squared divided by the coefficient of x cubed, or the negative of that, should I say. Assuming that a is not equal to 0 here, obviously. We've also got things like alpha beta plus alpha gamma plus beta gamma is equal to c over a, and alpha beta gamma is equal to minus d over a. So these are very useful relationships, but these can be extended to polynomials in general, so that the sum of the roots is equal to the negative of the coefficient of this term divided of this coefficient divided by this coefficient. In other words, this sum is going to be equal to minus 2n plus 1 choose 3 over 2n plus 1 choose 1. Okay? Don't forget the minus sign. It's important. So it turns out that this is equal to 2n plus 1 factorial over 3 factorial times 2n minus 2 factorial over 2n plus 1 factorial over 1 factorial times 2n factorial, which is equal to, let me have a think. So it's going to be 2n factorial over 3 factorial times 2n minus 2 factorial, which is equal to 2n times 2n minus 1 over 6, which is equal to n times 2n minus 1 over 3, which is exactly what we needed. How straightforward is that? Okay, that's the thing. Once you see things from the right perspective, it just writes itself. Okay, but the hard work comes from actually finding that way of thinking about it in the first place. That's it. Part 2 done. Okay, we're going to need that in a second, because now, before we use that though, we need to prove an inequality, which is that given that sine theta is less than tan theta for 0 is less than theta is less than pi by 2, prove that, this is not too difficult at all, cot squared theta is less than 1 over theta squared is less than 1 plus cot squared theta. Okay, let's do a bit more coffee. This is really straightforward, but it does rely on a certain fact that we've got to be aware of. That between 0 and pi by 2, sine theta, theta, and tan theta are all positive. This would not work if we didn't know that these were all positive, because if x and y are positive, with x less than y, then x squared will be less than y squared. Okay? So, in other words, because these are all positive quantities, then I get that sine squared theta is less than theta squared is less than tan squared theta. Also, be aware that if x is less than y, then 1 over x is going to be greater than 1 over y. So I get 1 over sine squared theta is greater than 1 over theta squared is greater than cot squared theta. Maybe I would be better off writing this as cosec squared theta. So therefore, cosec squared theta is 1 plus cot squared theta, no E3 identities, is greater than 1 over theta squared is greater than cot squared theta, which is exactly what we needed, just in the reverse order. Okay, easy, easy peasy. And then we will need this in a second. So what can I rub off? I'll clear some space there. So then, hence show that the sum of 1 over m squared from m equals, well, it will be 1, won't it? 1 to infinity is equal to pi squared over 6. Okay? So, what it might be tempting for you to do at this stage is, I guess, because we've got this relationship here, 1 over theta squared, maybe you're thinking replace theta with m, right? Because then we'll get, for example, 1 plus cot squared m is greater than 1 over m squared is greater than cot squared m. And then just, you can sum these, right? You get sum from m equals 1 to infinity of 1 over m squared greater than sum from m equals 1 to infinity of cot squared m, and so on and so forth. Uh-oh, we're going to have a bit of a problem here if we're summing over infinity. But let's just ignore that for now. This doesn't work, okay? For all sorts of reasons. One, we don't have a way of summing this, really. This, we've got 1 plus cot squared m. I mean, okay, it's going to be really difficult to evaluate that. You've got to be a bit more subtle about how you go about things, as it turns out. That's not the way forward. In fact, we do need to use this. Okay, so we've got the sum. I'm gonna have to look at my notes. What did I do? Oh yeah. So we know that the sum from m equals 1 to n of cot squared of this thing is equal to this. So therefore the sum from m equals 1 to n of 1 plus cot squared m pi over 2n plus 1 is going to be equal to n plus this thing, n times 2n minus 1 over 3, 3n plus 2n squared minus n over 3, which is 2n squared plus 2n over 3, which is 2n times n plus 1 over 3. Okay, so now that we've figured that out, we can come back to this inequality here. So we've got cot squared theta, so I'm going to write cot squared m pi over 2n plus 1 is less than, and it's going to be 2n plus 1 over m pi squared is less than 1 plus cot squared m pi over 2n plus 1. Okay, which now, okay, I'm going to sum from m equals 1 to n. I'm not going to sum all the way up to infinity yet, and it's important that I don't do that just yet. So I'm going to sum cot squared m pi over 2n plus 1 from m equals 1 to n, because I need these sums to be finite for the time being, is less than the sum 2n plus 1 squared over m squared pi squared from m equals 1 to n, which is less than the sum of 1 plus cot squared m pi over 2n plus 1 from m equals 1 to n. Okay, so clear some space. What can I get rid of? Ooh, I'm running out of space, aren't I? Let's get rid of, make a note of that. So it's n times 2n minus 1 over 3. I'm going to need that in a second. Okay, so this is going to be n times 2n minus 1 over 3 is less than, this is, now 2n plus 1 squared, I can pull the 2n plus 1 squared over pi squared out of this sum and just leave the sum of 1 over m squared from any m equals 1 to infinity, from m equals 1 to n here, which is less than 2n times n plus 1 over 3. Divide through by 2n plus 1 squared, then I get n times 2n minus 1, and don't forget the pi squared as well, over 3, 2n plus 1 squared is less than the sum from m equals 1 to n, 1 over m squared, which is less than 2n times n plus 1 pi squared over 3 times 2n plus 1 squared. Okay, so that's where we're up to for now. And now I can start to let things go to infinity, right? So I need to take limits through here. So the limit of this, the limit as n approaches infinity of this thing is equal to the limit. So I'm going to divide numerator and denominator by n squared. And what that's going to give me is 2 minus 1 over n times pi over 3 times 2 plus 1 over n squared. And the limit of that is equal to 2 pi over, pi squared, sorry, over 3 times 4, which is pi squared over 6. Okay, the limit as n approaches infinity of the sum of m equals 1 to n of 1 over m squared is the sum from m equals 1 to infinity of 1 over m squared. And finally, the limit as n approaches infinity of 2n times n plus 1 pi squared, blah, blah, blah. Divide numerator and denominator again by n squared. I get 1 plus 1 over n over 3 times 2 plus 1 over n squared, pi squared, which is equal to 2 times 1 times pi squared over 3 times 4, which is 12, pi squared over 6. Now, the next step, very, very important, and you've got to be very, very careful. What this shows is that pi squared over 6 is not less than this, less than or equal to. Okay? The sum from m equals 1 to infinity of 1 over m squared, less than or equal to pi squared over 6. So because I've got this is greater than or equal to pi by 6, but it's also less than or equal to pi by 6, that means that it must be equal to pi squared over 6, sorry. Okay, so this is, once you get onto university maths and you start doing a lot more in sequences and convergence and things like that, you'll learn this to be the sandwich rule. I kid you not, it's called the sandwich rule or the squeeze rule or something like that, where you've got effectively a sequence that's squashed between two other sequences, but the two other sequences have the same limit, and therefore the one in the middle must also have the same limit as these other two. So that's kind of the idea that's going on here. And that's it, okay? Again, you've got to show all this kind of stuff fairly explicitly, okay? You've got to make sure that your logic is fairly sound. How I've gone about finding these limits, there's different ways at A level that you might be shown. So you might be, for example, some people, I don't recommend this too much, but let's say I wanted to find the limit of this. What some people might tell you to do is just replace n with infinity. So you'll get something like infinity times 2 infinity minus 1 over 3 times 2 infinity plus 1 pi squared. So this is going to be equal to infinity times 2 infinity. Because 2 infinity minus 1 is just 2 infinity, evidently. And 2 infinity plus 1 is just 2 infinity squared. So I don't like this at all. So you get 2 infinity squared over 3 times 12 infinity squared, cancel. Oh, don't forget the pi squared over 6. Very iffy way of going about finding limits. You can kind of get away with it at A level, but once you get further down the line, you definitely won't be able to get away with stuff like that. So anyway, that's how you can figure out that this sum is pi squared by 6. So I was lucky that I hit on this fairly quickly, but I've got to say I did initially, when we first figured out that inequality, just replace theta with m. Sometimes just doing the naive thing just to rule it out is kind of worth doing, okay, so that you can kind of move on from it. I had a feeling that it wasn't going to be as straightforward as that, and it turns out it wasn't. So you've got to be a bit more careful with how you go about it. But that's it anyway. So we're done. That's the end of this problem. It's been quite a long video. An interesting problem, nevertheless. If there is anything that you're not clear about, please leave a comment in the comment section. Just ask any questions that you have. It would be great, by the way, if you could hit the subscribe button and share this video with anybody that you think might find it useful. So what I'm trying to do is to go through some problems from STEP papers, MATs, and old Advanced Extension Award papers and things like that. Really trying to help people that are preparing for these exams and that are hoping to go on to university to do, particularly, kind of high-ranking universities, to do mathematics or computer science or statistics, things like that. Okay, so it'd be really great if you could show your support by hitting the subscribe button and hitting the like button. And with that, I'm going to say thank you for watching and see you in the next video.